Hello, in this video I'm going to solve the following problem for you. Let X be a non-empty set and let delta denote symmetric difference between sets defined on the power set P of X as follows. For all A and B in the P of X, A delta B is defined to be as A minus B union B minus A. Prove that P of X and delta forms an abelian group. That would be a good idea if you pause the video at this point and give it a try yourself. Okay, so now we have a non-empty set and P of X is the power set, the set consisting of all subsets of the set X. We pick up two elements from P of X and define A delta B. In this way, we want to show that P of X forms an abelian group with this operation delta defined on P of X. The first thing we have to prove is to show that this operation is indeed well defined. In other words, my set is closed under this binary operation. Okay, that is very simple because if A belongs to P of X, you know that this means by definition A is a subset of X. On the other hand, you know that A minus B is itself a subset of A. Yes? So A minus B is a subset of A, and A is a subset of X. So from these two, I can conclude that A minus B is indeed a subset of X. Okay, but this is very simple, but if you want to do it rigorously, you can write something like this. So B belongs to P of X, the same story. B is a subset of X, then B minus A is a subset of B. Comparing these two, B minus A is a subset of B, B is a subset of X. So this means that B minus A is a subset of X. Then I can union these relations side by side. So it becomes A minus B union B minus A is a subset of X union X. Yes? But this is nothing except A delta B. And we know that X union X is X, so this means that A delta B is also a subset of X, but this means that A delta B belongs to P of X, because P of X is the set consisting of all subsets of X, including this particular subset. So closeness is actually done. And if you don't mind, because the next step usually is to check associativity, but because finally I am supposed to prove that the group is abelian, I have to show that this operation is commutative. I want to do this one first because I want to use commutativity to prove associativity. Because the associativity part, as you will see, it will be fairly long, so I don't want to repeat things. So this is why I want to prove commutativity first, which is completely obvious, yes? Because you can see that this operation is not sensitive if I change A to B, B to A. This becomes B minus A, this becomes A minus B, but you already know that the union is commutative. So you just write that. So you write A delta B, let us say A and B are arbitrary elements of the set. And then when I calculate A delta B, it becomes A minus B union B minus A. But I know the union operation is commutative, so I can interchange them. So B minus A comes first and union A minus B, but this is nothing except B delta A. So I showed that A delta B is always equal to B delta A. Okay, but the most tedious part is proving associativity. So proving associativity means that if I have three elements of my set, let us say A, B, and set C, they are arbitrary elements of my power set. I want to confirm that A delta B delta C is indeed equal to A delta B delta C. In other words, if I have two delta operations, one after the other, it doesn't matter how I group them. You can do this one first, or you can do this one first. Okay, let us start from here. A delta B delta C. What can I write about? Because you know that the difference is not a good operation to work with. Whenever you want to work with set theoretic difference, of course, it is a good notation to have. But whenever you want to discover any relation for subtraction of two sets, it would be better if I change it to intersection or a union so that I know a lot of theorems about them. So motivated by that, I will start doing the same thing. So what I will do, let us consider this set a new set D in your head. So then I will have A delta D. I will use my definition. D plays the role of the B. So this becomes A minus D union D minus A. Okay. But now let me do this part by part. For example, let me put this one star here and let me put double star here. Okay, so let us see how we can continue. So A minus D, I can write it as A minus, instead of D, I put this expression B delta C, but B delta C, using my definition, can also be written as A minus. Instead of B delta C, using my definition, I write B minus C union C minus B. Okay? But we have a very famous theorem in set theory. If I have two sets, let us say that I have a set X and a set Y. If I have the set X minus set Y, I can write X, change this to intersection. The price that I have to pay is to make this the complement. Okay, so I will do the same thing, but I want to give the role of A to this X, and I want to give the role of this to Y. So if I continue using that, I have to just copy and paste A. I change this to intersection, but I have put a complement there. Okay, but we also have De Morgan's law, yes? The one that we need here is if I have the union of two sets and I want to find the complement, I can find the complements separately, but I have to change this to intersection. So I will use this here by giving the role of B minus C to X and giving the role of C minus B to Y, yes? And I copy and paste, of course, the first part. So this becomes A intersection, the complement of the first one, intersect complement of the second one. Okay? Now I will use again this theorem with another version of the De Morgan's law. The other version is that if I have X intersect Y and I want to find the complement, again I can do them separately, but intersect changes to union. Okay, so what I will do here, so let me write it down, it's probably better. So I copy and paste the first part, but remember, B minus C, I use the first theorem, and I would write it B intersect with the complement of C. So B intersect with the complement of C, but remember, there is another complement up there, and then you intersect, and then I have C, I want to use the same theorem. I will copy and paste the first, change this to intersect, and then this becomes B complement. And then I also have another complement up there. Yes. Okay, so again, I copy and paste this part, but I will use De Morgan's law, the second version, here. This becomes the first one complement, the second one complement, but complement of the complement is the set itself, and this will change to union. The same story here. So it becomes C complement, union B. Okay? My goal is actually to expand as much as I can and write everything in terms of just union and intersection. One thing that I can do here, I can use distributive law to distribute union over, to distribute intersection over the union. So let me do it and then I will explain it. I pretend, because you know that you can pretend that this operation here is addition. Okay, you can pretend like that, a plus b, and then intersect is multiplication, c plus d. So do you remember when you want to distribute, you can distribute like this, yes? So I will do it, I can also do this, but I can justify it in a moment for you. So what I will do, I copy and paste this part, and I will start doing it. So I will take this one and intersect with that one as if I am working with polynomials, then union, this one with that one, then again union, this one with that one, intersect of course, and then union, this one with that one. Okay? And then I close. But this becomes much simpler. I will justify this shortly. So you know that this is the empty set. This is also the empty set. The intersection of any set with its own complement is the empty set. So empty set and union does not have any role. So I just have this one and the last one left. So this becomes equal to A intersect with the first one, B complement intersect C complement, and then union C intersect B. Yes? And now again, I can use distribution law. So A intersect with that, union A intersect with that. Okay, and I call that star. So let me write star here and put it to the box. So my star is now equal to A intersect A intersect, and by the way, when I distribute this in, A intersect B complement intersect C complement, I don't need to put any pairs of brackets because both operations will be intersect. So this becomes A intersect B complement intersect C complement. Yes? And then when I distribute this to the last, it becomes A intersect with C intersect B, again, because both operations are intersection, so I don't need to put pairs of brackets. So it becomes union, A intersect with, if you don't mind, let me write it in natural order, bring B first and C second. So this is something we were able to show. Okay? Okay, so let me justify what I did here, that I can do something like this. That is also very simple. If you have 4 sets, let us say, what was that? It was X union Y, and then intersect, let us say Z union W. I want to show that we can do that. Of course, you can take this in your head as some set A, and then this becomes exactly the normal distribution. Yes, so it becomes A intersect with Z union A intersect with W. Yes. And now instead of this A, you can put this back, intersect Z, and union, you can do the same thing here. So instead of A, I put X union Y, and then intersect W. And then you see that this is again normal distribution. Yeah, so I distribute this inside, and the same story here. But because now the operations between these groups is all union, I don't need to put any pairs of brackets, so it becomes union X intersect W and union Y intersect W. So when you look at the result at the end, it seems exactly like polynomials. So X intersect with Z, X intersect with W appears here, Y intersect with Z appears here, Y intersect with W. Of course, in numbers, the other way around, you know, is not correct. So if this operation is multiplication, this operation is addition, there is no way that I can distribute addition over multiplication. But you know that in set theory, if I change all unions to intersection and this one to union, this will work, but of course you have to change every intersection to the union and every union to the intersection. So it's a faster way if you want to do it. Okay. Okay, so let me clean this because we don't need this one anyway. Okay, so now what we are going to do, we want to go back there and talk a little bit about our double star here. So what was my double star? So the double star was D minus A, but what was D? D was the name I give to this, so it is B delta C. So it is B delta C minus A, but again, B delta C by definition is B minus C union C minus B, and then I have intersect A complement. Why did I do that? Exactly, I use that theorem again. Yes, that theorem. So giving the role of x to the first one, giving the role of y to the second one, you can write the first one, which is this, and change this to intersection and do the complement. But now, as you see, this is just the normal distribution because this is union, this is intersection, so I can distribute the intersection over the union from the right-hand side, it doesn't matter. So this becomes B minus C, intersect with A complement, union, C minus B, intersect with A complement. And again, I use the same theorem on top for this part and that part. So this can be written as B intersect with the complement of the second one, and then you have another A complement here, and then you have union. This also can be written as C intersect with B complement, and then you have another A complement here. Okay, so finally, this is the result of my double star, yes? So my double star is equal to, if you don't mind, let me just write them in order. So I will write, because all of them are intersection within the pairs of brackets, so I can write A complement, intersect with B, intersect with C complement, union, A complement, I write it first, intersect with B complement, intersect with C. So, and this is your double star. Okay, so now do you remember the set that I was looking into it is star, union, double star. So finally, the left-hand side, what happens? So the left-hand side, which is A delta B delta C, can be written as the union of these two parts. So I want to union this with that. It doesn't matter in which order I start. If you don't mind, let me start from here. So I would write A union intersect B complement intersect C complement. Instead of writing this, let me write these two first because all of them are union. I just want to keep it in order so that it is easier to remember for the future. So it becomes union. I will write this one, A complement, and then intersect B, intersect C complement, and then I write the next. It is A complement, intersect B complement, intersect C, and the last one, union A intersect B intersect C. So I was able to show that the left-hand side is indeed equal to that one. Okay. So it is already clear that it is associative because the operations of union, so I was able to express this solely in terms of union and intersection. But to really convince ourselves, we have to calculate this one as well. Okay. One way to do it is to go through this long process once more. And of course, then you will compare that both sides are equal. But the way that I want to do it, I want to start from here, and I want to use my calculation here and using commutativity, which I confirmed in the first step. So what I would say that the right-hand side is equal to what? Is equal to a delta B, delta C. But because I showed that delta is commutative, here, this becomes equal to if I write C first and then write this. So I use this commutativity to interchange these two sets. But now look, this set is the same set, but C is playing the role of A is playing the role of B, and B is playing the role of C. Because when I was finding the result of this expression, I assumed that A, B, and C are arbitrary sets. I can use the same formula for expanding this. But the only thing that I have to be careful now is that C plays the role of A plays the role of B, and B plays the role of C. So it means definitely the expansion of this will be the same with the changes that I mentioned. Which changes? So every C here should be replaced by A. Every A here should be replaced by B. And every B here should be replaced by C. Okay, so let us do that. So this becomes equal to, I will write this with those transformations. So instead of A, I put B, intersect, instead of B, I put C, instead of C, I put A, then union, instead of A, B, instead of B, C, instead of C, A, then union, B, C complement, and A. And finally here, A becomes B, intersect B becomes C, and C becomes A. Yes, this is what I get. But it is immediately understandable that they are the same. Yes, this is exactly the last term. So here, A intersect B complement C complement here. This one is A complement B complement C. So A complement B complement C. And then here, A complement C complement B. A complement C complement B. So hopefully you agree with me now that the left-hand side is equal to the right-hand side. So it means that the operation is indeed associative. The other parts are very easy. So for example, I want to convince myself that there is an element in the set, let me call it B, so that for every element A in the set, A delta B is A itself. In other words, I want to prove that there is an identity element there, and I don't need to check the other way around because I know the operation is commutative. But this is very easy. You just guess, and then you confirm your guess. What is the guess? It is not hard. You go to a scratch paper, and then write the definition of this. A minus B union B minus A equals to A. So you don't have to prove that theoretically what B is. You don't need to solve an equation and find your B, because you know that if you just guess the B and confirm that, it will work. Okay, so what do you think? What should I choose for B so that the left-hand side for every choice of A becomes A? I hope that you agree with me. It's not hard to see that the empty set will play the role. Yes, because A minus the empty set is A itself, but the empty set minus any set is the empty set. A union the empty set is A. So you say that we show that for every A in P of X, A delta the empty set is A, and then you start from the left-hand side. So by the observation you made in a scratch paper, you just claim this and prove your claim. So the left-hand side becomes A minus the empty set union the empty set minus A, but A minus the empty set is A, union empty set minus A is the empty set, and A union the empty set is this one, which is equal to the right-hand side. Now, finally, you need to prove that every element in the set has an inverse. What does it mean? It means that if I give you any A, you have to confirm the existence of another B, or probably an element in the group, so that the answer becomes the identity element. But in the previous case, we confirmed that empty set is the identity element. So you have to show that if you give me any set from the power set, I can find another set in the power set so that this result is the empty set. By the way, I have to confirm that this empty set is in the power set, but you know that the empty set is always in the power set of any sets, yes? Because the empty set is a subset of every set. Okay, now here, you gave me a set from the power set, and I go to a scratch paper. Let me divide this by 2. I want this time A delta B, which is A minus B union B minus A, turns out to be the empty set. Okay? But if the union is supposed to be the empty set, each one of these sets should be empty. And this is not very hard to show that if A minus B is equal to B minus A and B has to be the same. Okay? So if you know that little bit, it is not hard for you to guess that B is indeed A itself. So the inverse of every element is the element itself. Then you claim that, and then you prove it. Okay, so you say that let A belongs to P of X. We show that A delta A is the empty set. And that is very easy. You just calculate the left-hand side. Now you open it up. So A minus A union A minus A. And then this is the empty set, and this is also the empty set, and you want to union them. Of course, it becomes this empty set, and that is equal to the right-hand side. So the identity element of this group is the empty set, and the inverse of every element is the element itself. Okay, I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.